In 1965, a scientist at a U.S. national laboratory built a nuclear reactor that could not melt down. It ran for 13,000 hours. When it worked perfectly, he was fired. The reactor was shut down, not because it failed, because it produced the wrong byproduct for the Cold War. On November 1, 2025, China's Shanghai Institute of Applied Physics announced the world's first successful conversion of thorium into usable nuclear fuel. 60 years after Alvin Weinberg proved the concept at Oak Ridge, China proved it works at scale, using America's own declassified documents. To understand why thorium is different, you need to understand one distinction: fertile versus fissile. Uranium-235 is fissile, like dry wood, ready to burn. Thorium-232 is fertile, like wet wood. It needs a lighter to start. Remove the lighter and the reaction stops instantly. That single difference changes everything. In a thorium molten salt reactor, the fuel is dissolved in liquid salt. If the reactor overheats, the salt expands. The reaction slows automatically. The physics itself provides an additional safety mechanism built into the design. The reactor cannot run away because the chemistry prevents it. The most ingenious safety feature is the freeze plug. A plug of solid salt sits at the bottom of the reactor, actively kept frozen by a small electric pump. If power fails, for any reason, the pump stops. The plug melts. The fuel drains by gravity into a subcritical storage tank. Compare this to Fukushima. In 2011, a tsunami knocked out backup generators. Cooling pumps stopped. Without active cooling, uranium fuel rods overheated and melted. In a thorium molten salt reactor, a power failure is not a disaster. It is the automatic shutdown mechanism. Thorium is 3 to 4 times more abundant in the Earth's crust than uranium. It is found on almost every continent. It is a byproduct of rare earth mining, material currently discarded as waste. India alone has enough thorium to power the entire country for centuries. The energy comparison is almost incomprehensible. 1 ton of thorium can produce the same energy as 3.5 million tons of coal, 200 tons of uranium, or 4 million barrels of oil. A handful of thorium the size of a golf ball contains enough energy to power a human being for their entire lifetime. Uranium nuclear waste is a generational problem. Plutonium-239, the main long-lived component, has a half-life of 24,100 years. We are building storage facilities designed to last longer than recorded human civilization. The thorium cycle produces waste largely dangerous for centuries, not millennia. The difference is approximately 100 times. The volume difference is equally dramatic. Because thorium reactors can burn their own waste, and even existing uranium waste stocks, the net waste requiring permanent storage is reduced by approximately 90%. Thorium reactors can consume the long-lived actinides left over from conventional uranium reactor operations. The weapons question is honest but nuanced. Thorium itself cannot be used in a weapon. The uranium-233 it produces theoretically could be, but it is always contaminated with uranium-232, which emits intense gamma radiation. Any weapons program using thorium would be extraordinarily difficult, detectable, and dangerous to handle. In 1960, Alvin Weinberg began designing the molten salt reactor experiment at Oak Ridge. Construction started in 1962. It went critical in June 1965. By October 1968, it became the first reactor ever to run on uranium-233 produced from thorium. It ran for 13,000 hours and worked perfectly. The reason the program was canceled was not technical. The Atomic Energy Commission chose the uranium-plutonium design instead. The crucial difference, that design produced plutonium, and plutonium was what the U.S. military needed for nuclear warheads during the Cold War. Thorium produced no weapons-usable material. China did not make this choice. Starting in 2011, it invested $444 million in the TMSR LF1, the world's first operational thorium molten salt reactor. Built using declassified U.S. documents from Oak Ridge, construction began in 2018. The reactor achieved first criticality on October 11, 2023. The TMSR LF1 achieved 3 world firsts. The first thorium addition to an operating molten salt reactor in October 2024. The first conversion of thorium to uranium-233 fuel in November 2025. And the first fuel reload into a running reactor without shutdown. 3 achievements in 1 experimental reactor. India has taken a different path. Holding 25% of the world's thorium reserves, India designed a 3-stage nuclear program specifically to reach thorium power. Stage 1, conventional uranium reactors. Stage 2, fast breeder reactors to breed plutonium. Stage 3, thorium reactors fueled by the plutonium from Stage 2. Beyond China and India, a new generation of thorium companies is racing toward deployment. Copenhagen Atomics in Denmark is building a 1-megawatt pilot thorium molten salt reactor for 2026, designed to ship in a standard container. Chicago's Clean Core Thorium Energy has developed thorium fuel that works in existing reactors. Here is the honest challenge. Thorium has no fuel supply chain, no fabrication industry, no trained workforce, no regulatory framework. Uranium has a 70-year industrial head start with 440 operating reactors, established supply chains, and trained engineers worldwide. Building the thorium industry from scratch takes decades. The corrosion challenge is also real. Molten fluoride salt at 700 degrees Celsius attacks metal alloys. Oak Ridge identified this in the 1960s. China's TMSR LF1 is developing new corrosion-resistant alloys. Copenhagen Atomics replaces corroded components rather than preventing corrosion entirely. Neither solution is yet proven at commercial scale. America invented thorium nuclear power in 1965 and canceled it in 1972. China revived it in 2025 using America's own documents. Whether we chose the wrong fuel 60 years ago, and whether it is too late to change, is no longer a theoretical question.